Okay, science time. Today we are talking together, us, we all, y'all, me, and y'all, together, we, plural, the plural singular, first person, not plural singular, that makes no sense. Plural first person. We are discussing, we all, y'all, and me, we are discussing, oh, really interesting point, Mason. Are discussing light. Light. The objective, as you will remember, is analyze light waves. So let's please write that down. Our former objective was to diagram and model the properties of a wave, just waves in general, and now we are specifically talking about light waves. So please write that down. Analyze light waves. Analyze light waves. What is light? The sun emits light. Yeah. What is light? There are lights in this room. Yep. These emit light. What is light? Okay. It has to do with electricity. Is light the same thing as electricity? No, but it does have to do with electricity. So, what are some basic things that we could say are true of light in general? Okay. So we can perceive a brightness of it. I'll even put that as one of the properties of light, brightness. Okay. What else can we perceive of light? Color. Yeah. Are there kinds of light that are not visible? What would we call those kinds of light? Okay, that's one of them. Yeah. Invisible light. Visible and invisible. And let me tell you, it is not, it's a property of your eyes whether or not light is visible or invisible. And it's related to the property of the light. But the light itself is not inherently visible or invisible. It's your eyes that can differentiate between different kinds of light that are visible and cannot do that with. We cannot perceive light that is invisible. Some organisms, birds, some kinds of shrimp, some kinds of fish, have different ranges of vision, just like we had talked about how some animals have different ranges of hearing. Remember, we had talked about how human beings are capable of hearing sounds in the frequency range of 20 hertz to about 20,000 hertz. Human beings are capable of seeing wavelengths of light. Remember, wavelength and frequency are inversely related. Wavelengths of light from around 400 nanometers to I think about 4,000 nanometers, but don't quote me on that. But we do have a little math equation that helps us to understand, to relate the properties of waves in general to those of light. And that equation is V equals lambda nu, or lambda, I'll rewrite this as lambda f for you guys, because we did talk about frequency as f. So V equals lambda f. This is the general wave equation, where V is velocity, lambda is wavelength, and f is frequency. Frequency is measured in hertz, which is an inverse second, 1 over seconds. Wavelength is measured in meters usually, or some derivation of meters, nanometers, like I said, centimeters, kilometers, whatever. And therefore, velocity, if we multiply meter by 1 over second, we end up with a meter over a second, which is a unit for velocity. So those are how light waves relate. And since the speed of light is constant, V equals C equals 3.0 times 10 to the 8th meters per second in a vacuum. The speed of light in a vacuum is constant. I'm going to make this into a bow because it is a little bit more specific than that. We call that quantity C, which stands for constant. And that means that as wavelength changes, if V stays the same, as wavelength goes up, frequency must go down. If frequency goes up, wavelength must go down. So therefore, lambda, wavelength, and frequency, f, are inversely proportional. Remember, that's one of your CCCs, is proportionality. Scale, proportion, and quantity is one of the cross-cutting concepts. In this case, we're talking about inversely proportional. As one thing goes up, the other goes down. You'll even notice on this picture of scale, proportion, and quantity on the CCC, what are the examples they give? Elephant and mouse to remind you of scale, the differences in scale, and to remind you the differences, the colors of light. Because of the light we're familiar with, the visible light, the higher the frequency, more purple it is, the lower the wavelength. And the lower the frequency, the more red it is, the higher the wavelength. Let's draw a cool diagram. Let's start with red. Red, red, orange, orange, yellow, oh, I'm going to miss one. Yellow, green, oops, blue, I'm going to go in the closet for blue. One nice thing about that you guys can tell how prepared I am is I didn't even have all the dang colors of markers out, so that's something. Blue, shame on you. Blue, purple, 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 purple in the rainbow light show. Bright shining colors of the rainbow, rainbow, underwater rainbow. That little song is from a toy that my son used to have, and let me sing the whole thing for you faster. It said, and you can remember them this way: red, red, orange, orange, yellow, green, blue, purple, 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 purple. So it just says purple 5 times, which is really nice. So you can really remember purple 5 times as well as green and blue, but red and orange twice as good as green and blue. Anyway, this kind of light is what? We said the rainbow. Oops. Rainbow. We might call it a rainbow in our common parlance. It's the visible light. It's that part of the electromagnetic spectrum, the whole thing, what we call the rainbow and what we call visible light, that spectrum of light, all the different colors are there within contained, is only a tiny little smidgen, a tiny little portion of the entire electromagnetic spectrum. So the whole thing, light can have many, many, many different wavelengths and frequencies. Remember this, let me just remind you of this little pattern here. What about this wave that I have drawn is the wavelength? Yeah, the distance from one crest to the next is the wavelength. What about them is the frequency? Well, that is how many of them pass in a certain amount of time. What is the color of, what determines the color of our visible light? Yeah, well, the frequency and the wavelength. What determines the brightness, you think? What about this determines the brightness of the light? Red is brighter always? Can you have dim red light? Yeah, can you have bright red light? Can you have dim purple light? Can you have bright purple light? Can you have dim white light? So it is not velocity. For a given medium, light always travels at the same speed. It's this speed in a vacuum, but this, let me write this down for you too. You should write this down too. This decreases in matter. In fact, different kinds of matter have different speeds of light. It's not the speed of light that determines how bright it is. What other thing about the wave is there? What was it about sound waves that determined how loud they were? No, the pitch was the pitch. The frequency was the pitch for sound. We're missing one key component of this diagram.
It's like the little, it's the area between the line.
Yeah, it's that. What is that called? Amplitude. So the brightness of this is, you probably had your hands inside of your mouth, that's why I didn't hear you. The brightness is the amplitude of this. So the speed of light is the same in a given medium for this whole spectrum. The frequency and wavelength depend on where it is on the spectrum, but any of them can have a given amplitude. It can be brighter, more powerful. In this direction, we'll say, we're going to call this increasing frequency. And in this direction, we'll say, we're going to call this direction increasing what? What must it be? If this direction, if moving right on the spectrum was increasing frequency, what must be moving left on the spectrum? Increasing wavelength. Good. It is continuous in both directions. Also, increasing frequency necessarily means increasing energy. What would we call that light, which is a little bit lower in frequency than red light? No. So we have here, this is the visible spectrum. Below red, I'm going to kind of make these taper off a little bit more. Below has a word in Greek that you might remember. Below red would be that word red. You've never heard of this? Infrared. What about above purple? Can you guess what that might be? You even said it once before.
Purple.
It's above violet, we might even say.
Ultraviolet.
Ultraviolet. Ultra is the Greek prefix for above. Infra is the Greek prefix for below. Ultraviolet is that which is above in frequency from violet, and infrared is that which is below red. I hope someone's writing this down. Again, in the lower in frequency than infrared even, we have these microwaves. Microwaves. Below microwaves, we have radio waves. Which waves, that's where we end the spectrum. That's what we name all those waves below a certain frequency and above a certain wavelength. So far, which ones have the lowest frequency of those which we have written? Radio waves. And which ones have the longest wavelength? No, the longest wavelength, the biggest, the increasingest wavelength. Radio waves. So lowest frequency is highest wavelength. The wavelengths of radio waves are on the order of meters to kilometers. Sometimes the whole wave, even though it's invisible to us, is longer than a mile. They're very, very long waves. Okay? What about above ultraviolet? Well, above ultraviolet, we have these X-rays, and we have gamma rays. Gamma rays. And these are all kinds of radiation. They're all kinds of electromagnetic radiation.
Radiation?
The cool thing about electromagnetic waves, which light waves are, light is electromagnetic radiation. That's why when someone said earlier that light has to do with electricity, they were right. Electromagnetic radiation is light. The electric portion, the excitations in the electrodynamic field are given in this axis, usually is how we write it. And the excitations in the magnetic field come out and in. So I'm drawing these as dotted lines, but pretend like they're 90 degrees. Remember, this is a transverse wave. Remember transverse waves? Transverse waves are those where if the energy is flowing along this line, the excitations in the field, the wave crests and troughs are at 90-degree angles to it. They're perpendicular to it. You remember that? So light is a transverse wave, and you have to recognize there are two 90 degrees different from that. So if my here's my resistance band of science. Just ignore the other resistance band of science. I'm trying to tie a knot in this. I should probably get it closer to the mic so I can do ASMR with it. Here, come here. That's the sound of tying a knot in a resistance band, ASMR. Okay, so here I have my resistance band of science. Hold tight. If we say the energy is flowing from my hand to the Promethean board again, right? This direction, up and down, is a transverse wave. Do you remember that? Is there another 90-degree difference? I almost lost my eye. It's a good thing I have my safety goggles on. Put it back. Is there another 90-degree rotation that can be done from this axis? So once again, so we have up and down. That's our first 90 degree. What other way is different? Compared to me, left and right is also 90 degrees. So both of these are transverse waves. Do you see? In my diagram, the energy is flowing along this line. We might say from left to right, right? Correct? So up and down is one 90-degree axis, and in and out is the other. Okay? So here, if it's flowing from your right to your left, up and down is one axis, electromagnetic or electrodynamic, we'll say, and in and out is the other axis, magnetic field, we'll say. Does this make sense to you? So there's two. Nice. I could have broken the Promethean. I'm glad it didn't. There are two parts of an electromagnetic wave. There's the electro part and the magnetic part. Does that make sense to you? Okay. And that is light. What we call light, what we can see, this visible light when we're being scientific and specific, is only a small part of the whole spectrum. How do these light waves interact? Well, they can do three things. They can do three things. They can reflect, they can transmit, and they can absorb. be careful that you don't think of reflection only as a perfect mirror image. Remember, we talked about mirrors a little bit. A reflection, what would we call a reflection of a sound wave, by the way? Echo, an echo. A reflection of a light wave is a reflection. Is there a reflection anywhere in this room? Where?
The light is bouncing off the board.
Okay, yeah, I'm glad you pointed that out. Because I think you said the thermometer, or the thermostat maybe. Shiny, oh, you see a reflection off of this. But you actually see reflections off of all of this. Can I have your backpack?
Yes.
Look at this, Cameron. Look at this. Do you see this backpack? Do you know that since you see it, it is reflecting? Is this backpack emitting its own light? Not in the visible spectrum, probably. It probably is. Everything emits light, by the way, in some spectrum or some part of the spectrum. But since this is a low-energy object, it's probably way down here. But this green and kind of weirdly smelling backpack that I can smell from here is green because it is taking white light from where? Where's the white light coming from? What is emitting light in this room? Two things. The lights and the sun that's coming in from the windows. That's white light. You should know that white light is a composite of all the colors of light together. So white light is coming into the backpack. Here is backpack, 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 backpack. I know none of the other words to that song. Here is backpack. And here is, I'm going to use black to represent white. Here is light coming in. Remember, white light is made of all this light. What colors of light is being absorbed? All except green. All except green. So all of it is being absorbed except for the green. And the reason we see it as green is because the green is being reflected back. What color, let me ask you this question. What colors of light does a leaf absorb? All except for green. The green is reflected. So if you are, for some reason, starting a grow lab in your basement, for some reason, you're taking on the hobby of growing tomatoes in your basement. What color of light would you want to set up?
Green.
Yeah. Why not green? He's wrong. Why not green? What do the plants do with the green light? No, what do the plants do with the green light? They reflect green light. So they're not absorbing green light. That's why this is actually a grow light, by the way. It looks like a TikTok light here on camera, but it's actually a grow light. Don't look into it. It hurts your eyes really bad. What colors is it emitting? I can change it between different colors, but it can be blue, pink, purple. Purple, which is blue and pink, I guess, in this case. And it's because the leaves would absorb that color. So if you're trying to grow plants with artificial light, for instance in a basement, for instance any kind of plant, you would want the kind of light that is all of the colors except green, which is what this light is for. It has red in there. It has a little bit of orange and yellow, but not very much. Why would we not want very much orange and yellow? It's close to green. Yep. And then it has quite a lot of purple and blue. So red, purple, and blue are the colors that it's emitting mostly. Because those are the colors, the frequencies, the wavelengths, the colors, what we see as color, of the light that is emitting. Or sorry, that the plants are absorbing. So absorption is when light comes into matter and changes the energy level of that matter. Reflection we talked about. Reflection is when it's bounced off. There can be a perfect or an image reflection like in a mirror, or all the things that we see in this room that are not actually emitting light, we're seeing as reflected light. Our eyes are picking up the reflected light. What is transmission of light? Where is light being transmitted in this room? What's transmit mean? Transmit means go through. Go through. So where is light going through something in this room? The window. My glasses, yes. The lenses of your eyes, even you. You don't have these, none of you, because you're not dorks like I am. Oops. But these these lenses transmit and also refract, which has changed the direction of light. But even you cool kids, athletes that don't have glasses, have lenses, biological lenses in your eyes that refract light. Another thing, I'll kind of put a little caveat on this. Refraction is the bending of light. Bending. Some of us, cursed by God and Mother Nature, have to wear glasses because our lenses are misshapen, and so the light is bent in an abnormal way. The images don't form correctly on the retina. So I put these lenses in front of it to bend in the opposite direction to correct that. These are called sometimes corrective lenses. Does anyone in here wear contacts like a good person? I saw Joe's dad forcing him. Joe, you will not wear glasses anymore. Okay, bye.